Good evening, and thank you very much. I thank the committee for inviting me to speak here tonight, and I thank David for the kind introduction. Now, to get started, around the time of Captain Holland, this was a period after the French-English War, and England had gained a lot of new territory, and it was thought that this new territory would be very rich in commerce and agriculture, and so therefore they thought that there were very few surveys, in fact no survey of PEI, and so they thought it would be to great advantage to do a survey. So in this regard, Samuel Holland was appointed in London Surveyor General of His Majesty's lands for the Northern District of America. And that was in 1764. To come to North America, naturally the first thing that was needed was a vessel. They had no vessel, but found a vessel in the River Thames named the Canso, and it was moved to Deptford shipyard for refitting. The vessel was painted, ballast stored, topmasts and yards up, and made ready for the voyage. The total budget for the expedition was £1,818. Wouldn't be a lot of money for the time, I guess. On April 21st, the Canso cast off and stopped on the way to pick up guns, gunpowder, and 2 months' pay for the ship's company. After about 1 month, the Canso at sea, the Canso caught sight of the shore of Cape Breton. The whole voyage near come to a disaster, near just about when they landed, near shipwreck on the rocks off Satari Island. The only thing that saved them, apparently they didn't realize this, and they were about 600 feet from the rocks, and there was a fisherman at that time fishing amongst the rocks, and he saw them in peril, took an old musket he had and fired it, and warned them away from the shore. So that got them clear of that. Now, they sailed on to Quebec after that, and Captain Holland then left Quebec on the Canso with his crew from Quebec City and arrived at Port La Joye, now Charlottetown Harbor, on October 6, 1764. Prince Edward Island was largely uninhabited with an estimated population of 300 people, and that would have been just after the time of the expulsion of the Acadians. At the age of 36, Holland started the survey of Prince Edward Island. With Holland were deputy surveyors Arthur Robinson, Peter Haldeman, Guy Carleton, and civilian Thomas Wright. Captain Holland made acquaintance when he first arrived with Captain Ralph Hill at Fort Amherst, who would supply support in the months ahead. The sailors and most of the survey crew lived aboard the Canso. Captain Holland and his spouse, Marie Josette Roulette, had 10 children. Together they built a dwelling from a collapsed barn and salvaged boards. He provided a hogshead of rum for the workers, which no doubt helped ward off the fall chill air. Holland called the site of his home Observation Cove, and today is known as Holland Cove. From the site of Observation Cove, many observations were made by equal altitudes of the Sun and on Jupiter's moons. A sextant was used for these observations. This is a typical sextant of that era in the 1700s, probably similar to something he would have used. Soon after arriving in Prince Edward Island, Captain Holland wasted no time. And in the very fall, when he arrived, he started surveys right away. He put out small ships. They were larger than a whaler, and I don't know exactly what, but they got into a lot of trouble, I suppose, with the fall winds and storms, the same as we have those days, and wrecked a couple of them. However, the crew and the equipment was saved. In late October, the Canso was moved to Canoe Cove, and sailors and survey crews prepared for winter. Masks and rigging were removed and stored. With time on their hands, some sailors were disciplined for drunkenness, mutiny, and neglect of duty. In that time, a common form of punishment was whipping on the bare back. Wouldn't be nice at all, I wouldn't think. Note, besides rum, the only beer mentioned was called spruce beer, made from spruce needles and drank to help ward off scurvy. In mid-February 1765, Captain Holland sent out 4 survey parties. Each party was equipped with a single dog sled powered by a large dog purchased from the local Acadians. The dog sleds carried their instruments, maps, and supplies for an 8-day period. Sometimes it was noted that the crews got out, some of them, and got into difficulty, I suppose, winter storms, and couldn't get to them with supplies, and apparently sometimes some of them were near starvation by the time supplies got to them. There were quite often changes in the winter, and on reading some about it, I don't think the winters were terribly different than some of those winters we've been seeing. It spoke of periods of frost, mild periods, rain, sleet, and then back down to cold, which sounds fairly typical of our island winters. Now that's excepting this past winter, now mind you. There were changes in weather and very often cold temperatures. The average temperature was minus 12 degrees Celsius that winter. The coldest temperature of the winter was minus 21 degrees Celsius. Holland wrote that one soldier had been frozen to death and several lost fingers and toes to frostbite. One of his deputy surveyors, Lieutenant Peter Haldeman, was incapacitated by winter cold, forcing him to suspend his survey work. On February 9th, 4 consecutive days of observations were taken by equal altitudes of the Sun. These were taken to check the time of his astronomical clock. The clock is now stored at the Canadian Museum of History in Gatineau, Quebec. Much survey work was done along the shoreline from the ice. However, after the ice broke up and in early summer, the boats were sent out to complete the survey around the shoreline. After completing the survey in late summer 1765, finishing touches were put on a large-scale map of the island. Possible map, I think that's the map we hope to see at Confederation Center here this summer on display. This would be the map prepared from the results of Holland's survey, would have come from the results. Captain Holland divided Prince Edward Island into 67 lots and 3 counties with capitals for Queens County at Charlottetown, Kings County at Georgetown, and Prince County at Princetown. From these original maps, they certainly helped to create and make up, along with other things, the 1880 Meacham's Atlas. And that's a page when you open the atlas and the cover of the Meacham's Atlas. In September 1765, Holland dispatched Wright and Pringle to survey the west coast of Cape Breton. A month later, Captain Holland and party embarked on the Canso for the voyage to Louisbourg. For his work, Captain Holland was given Lot 28 in Prince County and organized some farmers and soldiers to settle it. Captain Holland's monuments are still standing in Victoria Park right to this day, from which he adjusted his compasses to magnetic north of 1764, on which his island lot layout is based. Note, interesting note, Captain Holland's pay for his daily survey work was £1 sterling per day. So, might translate into quite a lot in today's money, I don't know. It's a long while ago. Of interest, I apprenticed with the PEI Provincial Land Surveyor Robert H. Nicholson, who owned property at Holland Cove. Nicholson's family, descendants, still reside there today. I recall when I was assisting Nicholson on surveys at Holland Cove, an elderly resident said he remembered a house and barn on the point at Observation Cove. However, during the time of our survey in the early 1960s, had already been lost by erosion, possibly Captain Holland's residence. Could have been. It was on the point. I don't know those who know Holland Cove. There's the point of high land right at the point, and then it makes down into the cove, probably a drop of maybe 20 or 25 feet from that point down to the sandy cove. So that was possibly, may have been where his residence was. With today's instant communication, it is hard to imagine that the only means of communicating was mail carried by boat to different destinations, often taking weeks or months. Note that today's mail deliveries are often made all over North America in 24 hours or less. And wouldn't a cell phone have been of great help to him at that time? And a bit of email, perhaps. Dates of significance in considering Captain Holland's survey and lack of communication and transportation, just things I just noted. Father George A. Belcourt took the first car to PEI around 1866. Alexander Graham Bell filed the patent for the telephone on March 7, 1876. Wright brothers' first flight was on December 17, 1904. Northumberland Ferries' first crossing was June 28, 1941. So it was an awful lot of things when Holland was here, not even thought about or no notion of them at all. So I just found that kind of interesting in going through things. That is a wooden compass. That was common at his time, Holland's time of his survey, and may well have been some of the same type of compass that he used, possibly. In today's day-to-day survey work, with our data collectors, GPS control for latitude and longitude, computer systems, and AutoCAD for drafting plans and maps, every month, never a month in our office, that we still consult the 1880 Meacham's Atlas for the original divisions of PEI by Captain Samuel Holland. And this is the parts. There wasn't too many electronics, I don't think, to that. By the look of that compass, I don't believe. Holland College, a major educational institution in Charlottetown and continually expanding, was named after Captain Holland. That's about it for that. Some people ask me today, it's a little bit interesting too, are you still surveying? And I say, certainly I am. I'm practicing since 1968, about 46, 47 years on Queen Street. Well, they say you should soon be getting good. Well, I said, well, I say to that, time will tell. Thank you very much for your attendance.
Thanks very much. It's a real pleasure to be here, and I've really enjoyed meeting both Brian and David. It turns out that David's son Max and my daughter Kate grew up doing music together, but the daddies never met, but we finally met here. How many know what the moons of Jupiter have to do with this story? A few. Okay, well, I know a bit more than some other people here, too. There's an awful lot of knowledge in that audience, and I'll tell you the story here. Well, I need the... So Brian did a fascinating talk about the lay of the land, the surveying part, but the story of the moons of Jupiter is very interesting, and that's why I've been pleased to be part of this. I've learned an awful lot doing it. This is a picture I'll tell you a bit more about here. This is what the moon, if you look out at the night sky tonight when you go home, as long as the clouds allow it, you'll see Jupiter sitting up there. It's been up there all winter, the brightest body or star. I'll tell you a bit more about it. And you see 4 points of land, or 4 points of light, 2 on either side of Jupiter. Those are 4 of the brightest moons, the ones that Holland could see back in the 1700s. PI, after surveying in 1764 to 65, had a beautiful map, but they didn't know where to put that map on the surface of the Earth. All the surveying was done on land. They knew distances, they knew directions, and they had this beautiful outline that they'd done mapping the coastline. But they needed a measure of longitude and latitude for a known location on the island. Then they could drop that map onto a much bigger picture of eastern North America and put it together with Cape Breton and with New Hampshire's area, the northeast U.S., and then align the whole thing north and south, and then they'd have their bigger map. So what I'm going to do is review how latitude and longitude work to describe a position, and then I'll explain a bit about how navigators did that back in the 1700s. I have enormous admiration for Cook, Bly, and now Holland. I knew the other two, but I didn't understand their teacher, Holland. And they're an amazing group they could understand spherical trigonometry in their heads, and they could do logarithms in their heads, which is way above most of us. There we go. All right. Sorry, I apologize for fiddling around here. More than 2,000 years ago, and this is an amazing story too, scholars in Eastern Europe worked out a system of positioning on the surface of the Earth that they knew was spherical, based on a grid of east-west and north-south lines. So they've known that for a long time. In fact, one of Aristotle's students developed a map of the Mediterranean based on a north-south reference line, a prime meridian at the time, through Rhodes in Greece, and an east-west reference line, which would have been like their equator, that went through the center of the Mediterranean through the Pillars of Hercules at Gibraltar. So the world as he knew it then had a north and south and east and west quadrants. A few years later, another Greek estimated the circumference of the spherical Earth and actually got pretty close to what the real measurement is today with modern techniques. Given that he had no satellites and nobody at the time had circumnavigated the Earth, that's a pretty amazing feat. They had already divided circles into 360 degrees, so way back then they had all the elements in place for our modern system of latitude and longitude. The same one that Mercator made famous in the 1500s, working from his studios in what's now Holland. And Samuel Holland's map makers used 200 years later in the 1700s. And like Holland today, we locate a position on the surface of the Earth by its latitude or its angular distance north and south of the equator. I'll tell you a bit more about that in a minute. And its longitude, which was even trickier, angular distance east and west of an arbitrary line of longitude, which in the Greeks' day would have gone through roads, but today goes through Greenwich, England, because England had the biggest fleet. They kind of ran the seas, so they got to pick where the prime meridian went. The most famous line of latitude is the equator, a great circle made by a plane that cuts through the center of the Earth, perpendicular to the north-south axis of the rotation of the Earth, that gray plane. And where it cuts the outside surface of the Earth, that marks the equator. That's a great circle. The other lines of latitude are lesser circles that are made by perpendicular planes that are stacked north and south of that, going up towards the North Pole and down towards the South Pole. And where they cut the surface is a lesser circle, and that's a line of latitude. The modern reference line for longitude is the prime meridian, the 0-degree longitude that runs north and south through Greenwich that I just mentioned. Still on my list of places I want to visit because there are famous observatories still there with museums that have all this information. Back in his day, navigators did not measure latitude and longitude simultaneously the way we do today. I mean, I can pick up my cell phone over there and not only tell a time to the nearest second just by looking at it, but I can also read out latitude and longitude to the nearest second of arc, which they certainly couldn't do in their days, and I'm sure Mercator would have loved it when he went through the Straits of, Magellan would have loved it when he went through the Straits of Magellan. And in fact, it wasn't until the 1870s that a French naval captain invented the modern method of celestial positioning that gave a fix, latitude and longitude, sort of simultaneously, based on pioneering work that an American commercial captain had done in the 1830s. That's a whole fascinating story for another day, but well worth a chance to look it up if you ever get an opportunity. And then, of course, it was all made completely obsolete by the GPS within 100 years. So it took them all that time to figure out how to get longitude and work out how to do it with a sextant, and then 100 years later it was obsolete. Latitude, let me click on here. Latitude is relatively easy to get, and for hundreds of years sailors could get latitude, and so could surveyors quite easily, using a sextant or some device for measuring the altitude of the body above the surface of the Earth, and a set of pre-computed tables that took care of some necessary corrections they had to make. Latitude can be found, for example, using the sun and the North Star Polaris. Those were the two most common, particularly the sun, the noon sun. And with a little more calculation, they could use other stars, planets, and the moon when they pass the sky over the navigator. The sun rises in the east over there, and then it peaks that line straight out to the channel, out to the strait, is pretty much due south. And if you look, the sun is at its peak right there, so is the moon, and so are all the other planets when they pass over. That's called your meridian because it's due south of you. And that's what Holland was taking sights on in order to figure out the mean time. I'll tell you more about that in a second here. So what they were trying to do is they were trying to measure that angle HA that you can see. This angle here, that line, I'm standing here right now, and the line from the top of my head through my feet to the center of the Earth is a perpendicular line that goes straight up into the sky. But when I look out straight out this way, I can't tell if my geometric horizon is really 90 degrees to that line or not. I can't do it. It's just too much air doing this. But I can see the visible horizon, which is a bit below that geometric horizon. So one of the biggest corrections you have to do is a correction called dip. That's got to do with the height of your eye, the circumference of the Earth, and therefore you know how far away this line is. Subtract that, and you can get HA. It's a bit more complicated than that, because there's a few other corrections, but not many more. What I'm measuring is this whole angle here. And that angle here is the same as the angle from the equator to the body I'm observing at the center of the Earth. And that's the key to positioning. So, for example, to use a noon sight, all I need to know from a table that someone pre-calculated for my day is the declination of the sun. Right now the sun is starting to head back to the north again from the south. The declination is 23 south in the wintertime and 23 north in the summertime. So if I know my date, I know that declination. And so when I calculate that angle HA, I have to just account for the declination, and I get my latitude. That's what it boils down to. It's a little more complicated than that, but not by much. So that's how navigators got their position out of sight of land for years. They kept careful dead reckoning to know how far away from land they'd gone, but they had no real idea what their longitude was. But then they could easily find their latitude. So they'd sail straight out from England, they'd sail south, watching their latitude decrease, and then they'd turn left and go to Africa and hope they landed in the right place. And it was about that simple for a long time. Noon sun sights are inaccurate for very precise positioning. And the problem with that is that as the sun is coming to the peak due south of us back there, it hangs for a while very, very close, and it's hard to measure exactly when it's at its peak. So it's possible to be out a little bit either side of that. For the very precise kind of positioning that map makers at sea needed in the 1700s, guys like Cook and Captain Bligh was a brilliant navigator, just not so good at managing people. In Holland, they used a method of averaging the morning and afternoon sights, what they call the mean time. That's not the mean time that we use today. There's a different definition for it. All they're doing is taking the mean of the morning sight and the afternoon sight, and that tells them where noon was. So they know where noon was, and they can use that to set a local clock, and they know how many hours after noon they do an observation. So that's important in a minute here. They needed a way to measure time to the nearest second, and it was only in the 1700s, in his century, when clocks were being manufactured that could keep time to the nearest second. The problem is that he didn't have one of Harrison's clocks that they could use on a ship. He had a tall pendulum clock that I'll show you a picture of in a minute here, and it's made of wood and it's made of metal, and a temperature gets to it, and the pendulum swing on a ship would eliminate the accuracy of that clock. So the next step is longitude. Latitude was easy to measure, but longitude's a different story. In fact, I've got an excerpt from a 1500s seamanship book that says basically, forget about no one will ever figure out how to do longitude. It's well beyond any human technology. But fortunately, they managed to find a way. The sun appears to rotate around the Earth at a rate of 15 degrees of longitude every hour. So that simple thing is key. Its motion is so predictable that in the 1700s, a large staff of human computers, that's what they called people who did these calculations, a lot of them were clergy and a lot of other people that had time on their hands, but were well educated and can work out these logarithms and all that stuff. They'd compile all these tables. So pre-computed tables for nautical almanacs were being published then. They could be used anywhere on Earth to work out positions from observations of the sun, planets, and stars if the navigator knew his or her precise time to the nearest second. That's the key. Because 4 seconds of error is 1 nautical mile. Knowing the time, they could consult the tables and do calculations, allowing them to convert the vertical angle of the body that I showed you to the time and line of longitude. So in order to get longitude, you need to have a sextant, a calendar, and pre-computed tables like with latitude, but you need a clock too. So the problem of finding a practical way of measuring longitude at sea was so significant that the Throne in England established that longitude prize. You may have seen the movie. It's a well-done movie about how all of this came about. And at that time, though, if you watch the movie, there were several complex methods for getting time without using a clock. One of them was the lunar distance method, and the other was the moons of Jupiter. The lunar distance method used very precise measurements of the altitude of the moon, the altitude of a star, and the distance between the two of them taken simultaneously. So that took 3 navigators with 3 sextants all doing it at the same second. And then the pre-computed tables that the fellows sitting at their desks with candlelight had put together the year before, there's only one longitude on the Earth's surface where that lunar altitude, those 3 measurements would occur, so they would know a time. It typically took the team of 4 navigators 4 hours of work to do a single lunar measurement. Once the navigator knew the time at Greenwich, which is what lunars gave them, he could compare that to his estimate of local apparent time from a sun sight, and the difference between them was an angular distance between Greenwich and where he was, the difference in time. And he could convert that at 15 degrees of arc per hour for the sun's travel into an angular distance in longitude. This is what the moons of Jupiter look like from Charlottetown, from our location on March 21st. It would have looked very much like this to Holland back in January and February when he took his observations in 1765. And you can see the form. There are many more moons than that around Jupiter, it turns out, but these are the 4 you can see with very good binoculars or a recreational telescope. Galileo, 100 years earlier in the 1600s, had recognized that the 4 moons were very predictable in the way they moved, and he had proposed that it might be a way of using it as a clock. Pre-computed tables were written so that a land-based navigator could use the moons. You can't do this at sea. You can't observe these Jupiter moons at sea because there's too much motion. To determine a precise time at Greenwich, the tables predicted for a given date the precise time when the moons would appear and disappear from behind Jupiter, which took very precise measurements. A problem with this measurement, it didn't work at sea. It's not a stable enough platform, but land surveyors can do it, so that's where the brilliant maps of Paris came from and all the other famous maps that evolved in that era. This is Holland's clock, which is the other key to the story, the one that Brian talked about. That is it coming back this summer? Yes, I can't wait to see it. By the time Holland set out to map eastern North America for the English crown, very good clocks were being manufactured that could keep time at Greenwich to the nearest second. But they didn't keep it forever. They would drift out, and so they had to be rechecked periodically. In fact, in William Bly's logbook of the Bounty, which you can actually go online and read, someone in the southern states, I wrote him last month to say, thanks very much for putting this up. He's put the whole thing up, and you can read the whole story of Bly's trip from the Bounty right up to the mutiny, written in Bly's writing. And all of his brilliant observations that he did, because he really was a fantastic navigator. And at one point, his clock stopped. He had some pithy things to say about the crew that were supposed to be in charge of that detail. And he managed to get it going again by doing lunar distances. Once the clock was set, he could refer to the clock to get both local time and Greenwich time in order to work out longitude. Holland and the surveyors and navigators after him for decades continued to use Jupiter's moons and lunar distance method to check their clocks, because it took about 100 years for them to have faith in the clocks. Captain Bly's full logbook is available, as I said, and he had learned those methods from Holland and James Cook when they were all mapping together in eastern Canada, which is interesting. So then John Harrison, if you read his story, I won't spend much time on it, but he's a clergyman who got fascinated with the idea of trying to make a clock that could be taken to sea and wouldn't be affected by gravity and motion. And his last Holland number 4 down here on the right, I think, was one that Cook took to the Pacific and trialed for them. He did win the prize over Maskelyne's objections because they thought the lunar distance method would last forever. Now, the next slide, you can actually find online, and this is amazing what's online. This is an excerpt from the paper that Holland and the Astronomer Royal published with Holland's observation of the Jupiter moon's times, and I'll tell you more about it in a second here, on January 27, 1765. Imagine doing that at Holland Cove with a 10-foot telescope, with the temperatures we've had recently, with no electric lights, with nothing but a fireplace. They had to build a stone fireplace for that clock and keep it up against it and keep the fire going all the time to keep the wood and the metal at an even temperature so the clock would keep running at a good time. So this is the actual paper where he published his notes. And of course, he couldn't, nowadays today, I was doing this yesterday, I was emailing with a colleague in Australia doing some research, and he couldn't email anybody. He had to wait till his observations got back there, and then it took them years to get the paper published. So Holland's team saw the eclipse at 9 hours, 36 minutes, and 31 seconds after local apparent noon at his location. He'd done that with the mean time with the morning and afternoon sunset to check his clock. So he knew exactly to the nearest second after noon where he saw the moons go in and out. An astronomer at Greenwich, about 3 weeks later, on February 19th, saw that happen at 13 hours, 46 minutes, and 42 seconds after his local apparent noon. The difference is 4 hours, 11 minutes, and 49 seconds of time. 15 degrees per hour for longitude of the sun, and that gives you the difference in longitude from Greenwich to the west. That works out to a longitude of 62 degrees and 57.3 minutes of arc west of the prime meridian. In another paper that Holland published, he wrote about their observation saying that the first satellite of Jupiter emerged at 9 hours, 36 minutes, and 31 seconds mean or equal time. By bringing Mr. Short's telescope out of the warm room into the excessively cold air, the mirror became very dull, by which I lost my observation. So he's trying to see a precise, you can imagine from that picture I showed you how precise you'd have to be. But Mr. Haldeman was sure of his being good. They had 2 of everything. So now Holland had an estimate of longitude for observation Cove on PI, but how precise was it? It turns out his position was out by 11 miles. There's Holland Cove, just outside Charlottetown, the yellow pin that I put there. And down here is the yellow pin off Pinette Harbor, where the longitude and latitude that they published is located. So when he put the map of this beautiful map of PI that was so precisely surveyed on a large piece of paper with longitude and latitude, he was out by 11 miles. He was out 7 miles to the east and about 3 miles to the south. But given that he had no idea where he was on the surface of the Earth and that technology he was working with, that's actually incredible precision. Certainly state of the art. They were completely blind to their true fix. They were using a wind-up clock inside the house against a fireplace. The sun travels in 7 nautical miles of longitude in 28 seconds, so it would have been easy to be a whole lot more wrong than that. They were trying to observe the precise second of Jupiter's moon passing behind Jupiter at a distance of 628 to 928 million kilometers with a 10-foot telescope in the dead of winter, like we've just had, at night. There are a whole lot of errors that need to be accounted for, and actually this paper by the Astronomer Royal is pretty interesting. It gets in, and some of the other papers gets into the intricacies of physics and even the biology of the human eye that are pretty interesting to try and work out errors they had to account for. The observation at Holland Cove was 3 weeks earlier than the observation at Greenwich, and I'm not sure, but maybe that accounts for a little bit of it too. But I mean, how could they synchronize if they couldn't email each other and say, I'm doing it today and I got a good one, do it tonight. So then, what they had at the end of all of this work that he did over several years, starting when he was 36 years of age, was they had a whole bunch of maps of Cape Breton and the northeast U.S., and around Quebec and the St. Lawrence River, where Captain Cook had helped him out and done a lot of work, and across the island. And they had all these separate maps, and they had to put them on a big place. So they had those X's you see are the latitude and longitude fixes that they got with this incredible amount of work they had to do to get a simple fix. And today I can punch it up on the cell phone in seconds. I made a list of things they didn't have. They didn't have canned food, mosquito spray, SUVs, hotels, search and rescue systems, airplanes, computers, smartphones, electricity. So Brian can tell us a bit more, maybe, well, actually David can tell us a fair bit about the plane table and how that would have worked. This, we think, was a key instrument they would have used. These are pictures from the 1700s when the Land Surveyors were doing their surveys around the coast of PEI. But,
well, the plane table is one instrument that we used as archaeologists. Maybe it's because we were sort of back in Holland's time. But for doing small surveys of just a small, say, an acre or several acres and so on, using a plane table is very handy because there's usually not a lot of relief and so on. And when you set up your plane table, you make it level, and it's a board that's about, various sizes. They come in various sizes, but they're usually about almost 3 feet by 2 feet. And you put your paper that you're working on over top of that. You wrap it just like a parcel. And then your map is actually drawn right on the plane table surface as you're taking sightings. And you can see here the fellow on the right there, there's no alidade or telescope associated with that to magnify it, but rather just kind of a gun sight orientation. And what he's doing there is sighting on a particular landmark, and that would give him a particular bearing. And just simply when that's sighted, he's got that sighted on a particular target, you take your pencil and you draw it right along the line of the base of the alidade, or in this particular case, the gun sight, and that's marked right on your fixed board where your map is sitting. And every time you turn your instrument, the board stays constant. You take your compass and take a bearing on where north is, magnetic north, and so on, and you'll draw a line along that side. So everything is fixed on that piece of paper. And you can take distances. In this case, they're using chains, which were a way of measuring 66 feet. I think there's an image of a chain coming up. but it's a measuring tape, and in chains and so on, you could measure particular distances along the line that you had drawn for a particular land feature or a landmark of some sort. But when you're finished, you've got this sheet of paper on top of the plane table you take off, and that essentially is your finished map. And you can annotate it with observations as to particular landforms or characteristics or buildings or whatever. You draw those right on the map to scale. And I'm sure in this, and there's probably a number of different, there's architects and engineering scales that are used to give like proportionate dividers and so on, so that you can determine a particular scale that you want to use, like an inch to a foot or inch to 5 feet, and then everything you use that rule and measure it off to the distance that you've measured on your map. So you'll come up with a finished product in this map. Now we know that the map that's coming to us is a composite of a whole series of maps that was done, and these plane table maps would have been pieced together like a mosaic to create, as you can see even here, that larger map itself. They would be done probably at different scales for different areas, just depending on the particular detail they want for a particular area, but at some point they would have to be scaled down so that they would all kind of match up together. But very simplistic. It's one that in the archaeology business, if you wanted to survey, say, the front lawn out here using a plane table nowadays, it can be done very quickly, very easily. We've got a finished map when you finish all your measurements. It's right there. So that's that.
This is the local Blue Heron Power Sail Squadrons, a local volunteer affiliate of the Canadian Power and Sail Squadrons, and every winter volunteers here teach boating courses and navigation courses, including celestial navigation, and a non-for-profit organization. That's who I've got involved with over the years. Thanks very much.